data integration in life sciences, and I want to make a contrast between the traditional ways that we do that and some of the ways that we should think about doing it. Now, typically what happens when we do data integration in life sciences is we think about where we're going to put it. We think about the repository for those data first. And then we take the data in and we form them so that they fit that repository. And then we proceed to work with them from there. The part about that gets to be a little bit disappointing is we haven't thought about the data themselves first. We worried about the actual implementation of where those data are going to go. And only as a secondary consideration do we worry about what we're going to do with those data. That runs us into some problems because typically what we're doing is putting things into the bespoke schema for a relational database. And that makes the semantics of those data implicit in a schema. And that's a problem for us because that schema becomes quite brittle. What we'd rather do is think about knowledge representation first. Think about the information that we'd really like to deal with and the information we'd like to combine it with to solve our problem. When we do that, we end up with a representation that's going to help us solve those problems much better than the traditional ways of doing it. The traditional ways, of course, have their purposes. When we, for example, understand exactly the kinds of information that we're going to be dealing with, and we understand exactly the kinds of queries that we're going to be asking, those kinds of situations, although they're relatively rare, can be well done on traditional relational database systems. They were designed for that, for example, and there are 40-plus years of query optimizers that can make those situations go very fast. Sometimes, though, you don't know where the information will come from. You don't know the new information that needs to be assimilated with what you already have. And you really don't know a priori what the questions are going to be that you might have to ask to solve your particular problem. When the knowledge representation is very rigid, you don't have the opportunity to follow your nose, as they say, through those data to try to answer questions. So what you can do is think about representing information in a graph format. A graph, as you know, is a mathematical construct, and we've been working with in computer science for a couple of hundred years, actually. These kinds of data structures come from Euler, a couple of hundred years ago. So those things have been around for a while, and we know how to do the computation over those graphs. There are some issues with performance on graphs, and we'll get to those in a bit. But suffice it to say, in terms of representation of information, a graph representation is fantastic. And the reason for that is the mathematical construct that is a graph is a set of nodes and a set of edges. And the nodes, when you think about them, kind of look like circles if you're visualizing a graph. And those circles represent concepts. They represent the subject of assertions or sentences. Some nouns, for example, in a particular situation. In life sciences, the nouns are the familiar things, the familiar concepts like genes and proteins and diseases and patients and clinical trials and drugs and things like that. And the edges, that are in the graph are represented as things that look like arrows. They represent relationships between concepts. So what you end up with is a set of subject, predicate, object triples that basically correspond to assertions or things that you might take as facts in the life sciences domain.